All right, cool. So we can, I think, get going. So today we're going to be talking about CTC decoding and beam search, and this is some stuff that you're going to use on both your homework 3 part 1 and homework 3 part 2. And so to start to get into this problem, it's kind of helpful to think about the differences between homework 1 part 2 and homework 3 part 2. You might have noticed that both of them are kind of phoneme recognition, but there are some distinctions that are meaningful here. So homework 1 part 2 was a sequence classification problem, and we were basically recognizing phonemes. And importantly, those were time synchronous outputs. So for every input we had, there was an output for the same time step. In homework 3 part 2, it's a little bit different. We're doing a sequence to sequence problem, and although there isn't time synchrony, there is order synchrony between outputs and inputs. And the punchline here is that we discussed in class how there are a couple of problems that we're dealing with when we only have, say, order synchrony, but we don't have time synchrony. And namely, those are the problem of non-aligned inputs and outputs, and then also the problem of being able to represent like repetitions in our predictions. And then we're also going to go through the inference process for something like homework 3 part 2, and for this we're going to discuss using greedy search to do inference, and then also beam search. So first up is training. And just a quick setup here. Again, the big idea is that inputs and our targets aren't time aligned. So it's the fact that the size of our y's does not equal the size of our x's, but also that they're not like proportional really in any way. What we do know though is that they are order aligned. And then ultimately we're going to be compressing our predicted sequences, and then we also again need to be able to yield repeating outputs after this compression occurs. So it might be helpful to look at a picture of this. And so in this setup, it's a little bit different. We're not doing phonemes in this kind of contrived example, but the idea would be that someone says the word, say, zoo, right? And this is an audio waveform that we can convert into MFCCs and get time instant inputs. And then jumping down to the bottom of the screen, our target here is that we wanted to, say, transcribe the letters ZOO to spell zoo, and that we want to do it at these particular time steps. And so you can see, as we described, like one of the issues here is that there's no particular alignment between the x0, x1, and so on, and the various outputs at the different time steps. And then also the fact that we want to be able to have 2 consecutive O's as we spell out zoo. And again, the one kind of asset we have here is that we can assume order alignment. And the punchline that we're going to try and illustrate here is that we're going to use this thing called CTC, or CTC loss, to basically get time-aligned targets and really get a kind of, for our loss, we want a differentiable loss, and we're going to get something that's effectively the expected loss over all possible alignments that we might get based on our outputs and based on the target sequence that we have. So first, to just illustrate a bit the problem of repetition. So when we do this compression that we talk about, there's some examples in lecture, but just to go over it again, all of the sequences on the left will compress to the same sequence on the right, which is just ZO. And so even, for instance, if we literally have zoo, like the word zoo, which is the target that we kind of want, it'll compress to something that's incorrect here because the O's come together. And so the solution to this, which we introduced in class, is to bring in this kind of break character, and the notation might change a bit through the recitation, but here I'm just going to have a percent sign to be the break character. And so now when we insert a break character in between the Z's and the initial O, we get a break, so it goes from Z to O. But then also when it's in between the two O's, we get a repetition there. And then, oh yeah, go ahead.
I mean, was that one, the first percent sign necessary?
It's not. But that's just to illustrate you can have one and it can still transition, and that'll come into play later. So yeah, but that's a good question. So again, the break character is our solution to this repetition problem. And then the problem of alignment is basically the fact that there are many different alignments that can map to the same correct output, or the same target, really. And so the question becomes, if we want to use a time-aligned target to compute a differentiable loss, basically which alignment should we choose? And we went over in class a couple of different potential solutions. One that might work well is using something like the Viterbi algorithm to find the most probable path, and then use that to calculate a loss. But we actually mentioned that there's a better option here, right? And it's using the kind of asset we had of order alignment, in addition to some of these kind of additional rules or properties that are part of CTC loss. And with that, we can go over all possible alignments and then calculate actually an expected loss over them. And so a quick aside on some of these additional rules, or like the properties of the CTC alignments that we might get, is number one is monotonicity, right? So once you kind of advance to the next input, you can either keep the corresponding output that you had or advance to the next output. And we'll get into this with some examples of this in a bit. Also, as we mentioned, like this relationship is many to one, right? There might be many different input elements for a single output element, and then kind of along with that comes three, that the length of the outputs is going to be less than or equal to the length of the inputs. And so putting this all together, the idea is, given our solution of a break character for repetition, given the order alignment and then some of the additional rules we had, we want to find the possible alignments, some probabilities, and then calculate a differentiable loss that represents kind of an expected loss over all these different alignments. So going back to our setup of just removing a bit of the noise from this page, our model output probabilities at each time step, and then we wanted to transcribe zoo at these specific time steps. That was our target. And really what the model's outputting is just kind of a probability distribution over the tokens or characters that that are our options. But in this case, actually what we're going to do is we're going to limit only to the characters in the target, and then also have breaks inserted. And so this is maybe a little bit more easily understood with something like this, which we start from the start of our sequence with nothing in it. And then at each point, you're saying, okay, it can be any one. You have a probability distribution, basically, over these characters. But you might notice when you look at this that based on some of the rules that we introduced, for instance, monotonicity, all of these paths aren't necessarily viable, and they're also not viable because you won't be able to get to the actual end of the sequence in time. You won't, if you just have a break character the whole time, you won't be able to get to the final O, for instance. And so we want to go through and figure out which of these paths are actually viable. And so for me, at least, it's helpful to think of this kind of from the outer edges into the middle. So let's start with these candidate paths. Does anyone here want to take a crack at which of these? So knowing that we have to start with either a break or a Z, and then end with either an O or a break.
Right, so the first two in the beginning stay.
Yep, exactly. And then for the next layer, this gets slightly more complicated. One thing you'll notice here is that some of these paths go directly kind of horizontally from a break to the same break. Some of them go one down, so from a break to the Z, for instance. And then here you can see that it goes from a break to a diff to the next kind of break, right? And so a question for you guys is that a viable path to take, right? Why would that not be?
Doesn't make sense.
Right, because you'd skip the Z, and then you're all of a sudden, you don't actually have a sequence that really replicates the target, right? And so that's exactly what we just said, where this might seem like a viable path at first, but it's really not. Conversely, you can go kind of what you brought up, Josh, about the question earlier of, was that break character necessary between the Z and the O? It's not necessary, but it's okay, right? You can go directly from a Z to an O. You can also go Z to break to O, and it's the same thing at the end of the day, right? So that's why that one's there. So then next up, we can do an example where similar logic, this path won't work because it's going to skip the first O, and then we won't be able to have a repeating O. And then finally, this path was sort of mentioned earlier, but it won't work because you won't be able to get to the final character in time, right? And so just to highlight again, like the viable skip alignments are bolded here just to give you a sense of where they are. But as you'll see, right, there aren't skips aren't kind of available for every place where they might exist, right? And you'll see in the homework, we'll actually ask you to keep track of when these skips are possible, and that'll help with your kind of forward-backward calculations. So these are all the possible alignments. And then what we actually want to do is kind of calculate this posterior probability of reaching a given node through all the possible paths that might go through it. And this, I think the professor went over this pretty in depth in class, but this is where we use the forward-backward algorithm. And these probabilities, these posterior probabilities, are what will allow us to calculate this expected divergence across all these possible alignments. And the good news, the punchline, is that now we can train. So we've dealt with the issue of non-time-aligned inputs and outputs. We've dealt with the issue of repetitions that we need to be able to represent in our outputs. And we have a differentiable divergence function that we can use to train our model. And so just to kind of summarize here, the training procedure is you'll define a model. It can really kind of be whatever you want it to be, but maybe in the homeworks you'll use a deep bidirectional LSTM, for instance. You initialize it to output both the target characters and a break character, pass your training instances through, get the probability distributions, construct your graph of those viable alignments or paths that you might go through, get the posterior probabilities using the forward-backward algorithm, get your expected divergence, backprop, and update, right? And so this is a nice procedure where we can train our model even when we have non-time-aligned outputs. And so again, just to kind of reemphasize the picture here, this is what you'll be more or less doing on the homework, and you'll start to see how the different modules in your code align, and then hopefully you'll also be able to understand what, for instance, in PyTorch, like the CTC loss is actually doing. So any questions? I'll pause there for a sec.
Just a general question, like, so this is better or performs better than the Viterbi algorithm?
Yeah, like the Viterbi algorithm, it's a little more kind of arbitrarily selective of just at a given point, like what is the best path through. This is basically a weighted average over all the paths, if that makes sense.
A weighted probability.
Yeah, or like a weighted loss over. So the expected loss is basically taking the posterior probability at each node in that graph and then multiplying by the log probability of the output, if that makes sense. Cool. So if no one has any questions on Zoom, we can move to inference.
Okay, so the main difference from when we do training to when you have inference is essentially during inference, you're not going to have a target to essentially compare. And there are no specific rules for the sequence that you have. So how do you necessarily deal with such a thing? And we're going to see how. We have multiple options. One of them is greedy search. There's also the exhaustive search, but considering the number of possibilities that we have, this is not really very viable. And of course, we have the beam search. And in your homework also, you'll be implementing the greedy search and the beam search. So let's see how that's done. So like the name says, in case of greedy search, of course, it's very straightforward to implement. It's very easy. You basically select at every time step what is the most probable sequence. You know that your model is spitting out some probabilities. You just pick across all the symbols what is going to be the most probable one. Of course, yes, implementation-wise, this is very easy, but it's not really very efficient because even though at every time step you're picking the most probable symbol, the overall path that you take might not be the most efficient one or something that makes sense when you actually look at the output. Nevertheless, let's look at, whoops. Let's look at how greedy search performs. So if these are your symbols towards your left, and at each time step you have this particular set of probabilities, at every time step you're essentially going to pick, like I said, the maximum probability. So at time step 0, you essentially pick A. At 1, you pick B. At 2, you pick A again. And at 3, you pick B. So you're simply doing an argmax of sorts to look at what is your final decoded string. And the final probability of the entire path is simply going to be a product of all of that. Now, you could have had a better path, which makes more sense, but greedy search really limits the ability to give you something that's meaningful. And this is why, even though this could give you pretty good results, we use something called as beam search. And Gabriel will be talking about that.
Okay. Hello. I hope you
We can hear you.
Okay.
How do I stop it?
Can you stop sharing so that I share my screen?
Oh, okay. Thank you.
Gabriel, are you able to start sharing now?
Yeah, I can start sharing.
Okay, let me share my screen. Okay. Hopefully everyone can see my screen.
We can, hold on one second.
Okay. Yes. So as Harini rightly mentioned, the
Gabriel, hold
the
on one sec. We actually can't see it.
can you hear me?
Oh, yeah, I think we can see it.
Okay, now it's
Yep.
perfect.
Thank you.
All right, cool.
Okay, so as Harini rightly mentioned, with the grid search, we are just selecting the max probable of each sequence, but for each time step. But if we're about considering the whole sequence, then most of the times it might actually not be the most likely sequence, So we are definitely limiting ourselves to some other future sequences that could be better than the one which we have using the greedy approach. So with the beam search, at every time sequence, we are trying to find the top k most probable prediction. So for example, if we are choosing like k equal to 2, then it gives us the possibility of going with the two most likely predictions, which could also have like have a higher sequence probability other than just selecting one like the greedy approach. So in this case, we start with, let's say, if we are dealing with a sequence length of 4 and a beam width of 3. So the beam width indicates how many top predictions we want to consider at each time instance. So here on this example, we have our symbol set, which is the same as that which you've seen before. And if you've seen the output from the greedy decoding, and now we will try to use the beam decoding. So for the very first time instance with beam width equal to 0, then we calculate the prediction score. So if at t equal to 0, then here we consider the output of the softmax, the probabilities of all the predictions. So with the greedy approach, we are definitely going to choose maybe A as our next predicted token in the sequence to continue with. But with the beam search, it's telling us, okay, we are not just going to choose A, but we are going to choose the top 3. So here we calculate the scores, and then we choose the top 3, which in this case it's going to be A, B, and C. So these are the paths which we are going to continue our decoding in that direction. And so it gives us the possibility of seeing other sequences that can actually lead to a high sequence probability. So for t equal to 1, so if these are the outputs of our softmax, then again we are going to consider the sequences which we chose before. Okay, so before our best paths were A, B, and C. So we would start from A and we would try to extend A with the predictions at this time instance, and then choose the top 3 again, since we are dealing with a beam width of 3. So we are going to calculate the new sequence score, which is getting the score which we have times the probability of having that token as the next token in our sequence. And in this case, once we calculate that, then we choose again the top 3, which is A extension, and AB and AC. So we'll continue this process over and over for t equal to 2 for all for the length of our sequence, and we would get like a new path. And remember, at any time we're choosing the top 3 or the top k, which corresponds to your beam width. So unlike a greedy search, you can automatically see here that if you have like a higher beam width, then it will take a longer time for your model to decode, because you would need to be going with all the sequences. And with greedy approach, it goes with maybe just one sequence. And that's the process. We continue that process until we exhausted all the sequence lengths. And here is the pseudocode implementation, which will be shared. And I think you've also seen this in your homework. Please, if you have any question about it, you can post on Piazza or ask during office hours. So in summary, here is some sort of like visualization. So if we have like if we are trying to decode the output of our decoder, then of course we would always start with the start of sentence token, which is given as the input for us to start predicting the next sequence. And here, using a beam width of 3, we can say this sequence, A, B, and C, they have like the top 3 probabilities. And in the next predicting the next token, again, we consider the top 3. For these other parts, we can already like ignore them because they are not in the top 3. So we would consider these other top 3. And at the end, we would calculate the sequence probability for all of the sequences, and we would choose the best one as our most probable sequence. I think that should be all. And if there are any questions, please feel free to ask.
Yeah,
So,
one question.
okay, there's a question on chat. Why do A, B, and C have the same probability of being chosen? Are you talking about this slide, Claude, on this slide, or it's in the previous slide?
No. Before we were taking a before this.
Yeah.
No, go. No, continue the next page. This one.
Yes.
I can see that in the calculation of the score, like we are multiplying the same, like this 0.257. You said it is the probability of this token to be chosen as the next in the
No,
sequence.
it's okay. So once you're decoding, right, your decoder outputs the probability of each token in your vocabulary. Okay. So for your vocabulary, if you are dealing here, our vocabulary is dash A, B, and C. Okay. So in that time sequence at t equal to 1, the output of our decoder, which is the final output after the softmax layers, says that, okay, A has a probability of this, B has a probability of this, and C has a class probability of this one, right? And now I am choosing the top 3, right? So if I look at the top 3, this is the first, which is B, right? And in my previous sequence, if I consider that I had A as one of my path, right, then the next one could be B, right? Yes, and if I have A and I can extend with with the dash, okay, and same with C. It happens for all of these. So we've taken the best parts which we have. That's why you're not seeing this dash as in the beginning, because in our previous search, the best parts were A, B, and C, right? So here we consider all the combinations, all the extensions of A, B, and C. Okay. And once we consider that, we would calculate the new score. And from the new score, which are these ones, right? Which we get like the previous score times the probability of the new token, then we would get the new score. And if we rank these new scores, then we would see that the most probable path, okay, sequence is now AB, AC, and A hyphen.
So the problem is why do we have the same probability as, I mean, this is 0.57 for both A minus, B minus, and C minus.
Because here for that class, for that time sequence, for that time period, right, that time instance, the probability that our next token is this minus, it's 0.257, okay? So considering that my previous token was A, right? And now they're telling me that the probability of the next token being a minus, it's then A times minus, okay? So this 0.257 comes from that present time, okay? And these other values comes from the previous best path, which you've already have.
I understand.
Okay.
One quick question.
Yes.
So here in time step 1, the maximum score is given by the sequence AB, right? So this also comes from the greedy approach, like greedy search. A has the highest probability, B has the highest probability, so AB combined together also has the highest score. So what is the
Yes.
benefit of beam search?
Okay. So let's say in this previous step, right? let's say if the highest probability here was something else, okay, it wasn't A, if it was the blank, right? Then we would go only with the blank, ignoring that. Then in the next steps, right, the other probabilities for having the blank and A can be lower than having A and the blank. Okay, so for the advantage for the beam search is that it gives room to consider a future sequence, okay? But with greedy, it goes just with like the current best sequence it has, okay? So irrespective of the probability. So right now, okay, if you look at this, we have this is AB, right?
Yeah.
In having AB, okay, let's try to see if actually so the greedy approach would have also chosen AB, okay? But if the previous highest probability wasn't A, the greedy approach would not consider AB, okay? So you going with the top three, right, gives you room to look at the probability that the future sequence, the probability of the future sequence can be greater than you just selecting the current maximum. I don't know if it.
But the beam will also choose the, if it's initially at T0, if the blank is the highest probability, then in time step 1, it will be one of the sequences with blank in the like t equal to 0. It
Yes,
has to be, right? So what is the
yes.
point then?
Okay, like let me try to explain it maybe with an example, with maybe another example. Okay, so let's say you leave your home and you're going to school, right? There are two possible routes, and you know that from route A to route B it's shorter, right? And your school, let's say your school is at location D. So from route A to route B, it's shorter. So that's the current knowledge you have. But from going through route C and from C to D, the overall distance would be shorter than going through from route A to B and from B to D. Because from B to D can actually be very long than you expect. Okay. So if you're going with the greedy approach, you're going to go through the long route. I don't know if it makes sense. But if you're going with the beam approach, you would leave room to also explore that, okay, and there could be a shorter route from going from A to C and from C to D.
Okay, okay. Later on in the sequence, it might change. Okay.
Yes, because the probabilities of the tokens are changing. It's not like it's fixed, right?
Okay, yeah, got it. Thanks.
Okay. Any other question? Okay, is there something on chat? So what is the intuition behind A blank or B blank or C blank? I couldn't understand very well. Please, can you maybe try to elaborate more, Claude?
Okay, I was trying to understand what star minus means, but you said it's a blank. Does it mean like, is that if you have A, the next token is a blank, like nothing is following? Is that
Yes.
minus? Okay.
Okay, if no other question, then I can stop sharing and pass it over to Quentin and Harini.
Alrighty, I think that basically brings us to the end of the recitation. So we can stay for a bit to answer any questions you guys might have, but other than that, yeah, should be good to go.